This one is fairly short, but really useful. So the idea is you want to find a normal vector to an equation of a plane. All right, so let's just say you have an equation of a plane. You have x minus 2y plus 3z, and let's say it's going through the origin. All right, so one way you can also write this, so let's say you have, your plane in 3D space, and let's get, a visual aid here. All right, you got your plane in 3D space, some orientation, whatever. A normal to the plane is something that points, straight out of it, is forming a right angle with every single vector that's in that plane. Right, and it's a normal everywhere on the plane because the plane's flat. You can rotate it, you can move it, whatever. Oops. All right, so we want to find that normal. All right, well, kind of the straightforward way to do it is we could solve for a couple of points in this plane, we could compare a couple of vectors, we could do a cross product, but that's a lot of work. Turns out there's a much, much easier way to do it. All right, so let's say you have some plane, and I gotta try and draw a plane. All right, and then you've got a normal vector on that plane, and you're forming, it's a normal right angle. All right, and it's x minus 2y plus 3z. Well, okay, what if you have, the first thing is we actually have x equals y equals z equals 0 is a solution. Right, this particular plane is going through the origin because we have this equals 0. All right, but let's say we have two more solutions. So let's say we have this dot right here. That's x1, comma y1, comma z1. And when you plug in these numbers, x1, y1, z1, into this equation, they end up equaling 0 when you multiply them out. All right, we could have another dot somewhere, right here. That's x2, comma y2, comma z2. All right, and so if you plug in these numbers, x2, y2, z2, in for x, y, z in this equation, you'll get this minus that plus that. It'll end up canceling out, it'll all be 0. All right, so another thing, though, is we could rewrite the equation for this plane as a dot product. So this is the same as, so the coefficient here, I have 1 times x plus negative 2 times y plus 3 times z equals 0. So I have 1, comma, negative 2, comma 3, and I'm dotting that with x, comma y, comma z is equal to 0. All right, since it's equal to 0, that means you have, it's perpendicular, right? And then if you want to write this in the notation for linear algebra, you would have 1, comma, negative 2, comma 3. So that row vector times this column vector, x, y, z, equals, ends up being just a single matrix, the 0 vector. Sorry, the 0 matrix. All right. So what this is telling us is that if you pick an xyz that solves this equation, then that xyz vector is going to be perpendicular to 1, negative 2, 3. So for instance, we have this x1, y1, z1. I have 1, comma, negative 2, comma 3. That dot product is going to be times x1, y1, z1. It has to equal 0 because x1, y1, z1 solved the equation. It's a point in the plane. But same thing with x2, y2, z2. x2, y2, z2. That also equals 0 because x2, y2, z2 lies in the plane. And so what this is actually telling you is that 1, comma, negative 2, comma 3 is a normal vector. To the plane. So that's a very, very nice shortcut. If you have an equation of a plane and you need to figure out a normal vector for it, a normal vector to that plane is going to be the coefficient in front of x is the first component, the coefficient in front of y is the second component, the coefficient in front of z is the third component. And now you might think, okay, well, this might change a little bit. What if this plane doesn't equal 0? What if it equals, 4? What if I have x minus 2y plus 3z equals 4? Well, it still doesn't really matter. So the plane that you have, let's see. All right, so let's say I'm in, I think I have enough hands for this. Right. Let's say I'm in, let's see, red, green, blue, XYZ space. All right. And I've got my plane, and the plane actually goes through, let's see if I can do this, the origin. All right, so one of the solutions to the plane is going to be 0, 0, 0, meaning, you have some number times x plus some number times y plus some number times z equals 0. So that's the normal vector here. What happens if you change this number 0 to something else, it ends up translating the plane, but it doesn't rotate it. So if you were going through the origin before, and you add 4 or something, you might end up over here. So you're no longer going through the origin. I'll try and make it a little nicer. You're no longer going through the origin, but you still have kind of the same slope. You have the same normal vector. If I shift this, if I move it, translate it, whatever, I always have the same normal vector. So I could be going through the origin, I could be, a little away from the origin, I could be kind of behind it. It doesn't matter, the normal vector is always the same. So, even if you don't have x minus 2y plus 3c equals 0, you have x minus 2y plus 3c equals 4, the normal vector is still, what is it? 1, negative 2, 3. It's one of the normal vectors. There's an infinite number, infinite length, backwards, forwards, but it still works. So yeah, as long as you have an equation of a plane, you can get it in this form. You could have, 0x plus 2y minus 3z, something like that. But as long as you have the plane equation, you can read the normal vector right off the coefficients in front of x, y, z. And it doesn't matter if it equals 0 or equals some other number. It's still going to have its normal vector come from here. And that's all because you have this dot product between the coefficients and all the points that solve the equation for the plane. And if a point in the plane solves the equation equals 0, that's going to mean that this vector is normal. Right? And you can end up translating this plane by changing, x, y, z slightly, or you can kind of absorb the 4. It's a little annoying to do, but it does work. This still will be a normal. When you add 4 or subtract 7 or whatever, it just moves the plane. It doesn't rotate it. So that's that. So it's very useful to have, and you can make a normal vector to a plane very, very easily. There's another thing you can actually describe. So can describe a plane using a normal vector and a point P in the plane. All right. The reason that's an alternative way, you could either use an equation or you could use a normal vector and a point P in the plane, is if you have a normal vector, so my little yellow vector, and I know that there's a point in space that the plane goes through, so I know it goes through, let's say, this point right here. So I have my normal vector, and it's going through that point. There's only one plane that is both normal to this little vector I'm holding, and it goes through the point at the tail of the vector, where I'm holding it. And so it's another unique way to describe the equation of a plane, all the points in a plane. You specify a normal vector to that plane, you specify a point in that plane, and then from that you can tell every single other point in the entire plane. All right, so this will come in handy, and there you go.